Afternoon, everybody. I'm Natalie Fowler. I am the ecologist on Unmanned Game Reserve here in the Eastern Cape. Today, I just want to give you a little overview of a project we started recently using drones, orthomosaics, and artificial intelligence to help monitor our vegetation. Okay, so just a quick overview of Amakala. It's a private game reserve between here and Grahamstown. It's a relatively small reserve, about 10,000 hectares in size, and we were established in 1999. Prior to the establishment, we was farmland, so we had beef, chicory, sheep, goats, irrigated lands, dairy, pineapple, you name it, we had it on the farm. And this very much has influenced our vegetation and just the overall landscape of the reserve. So just a quick overview of our vegetation types. Again, these aren't necessarily true representations of each of these vegetation types because of the historical land uses, but we've also adopted a very fine scale vegetation map. So we've got 8 different vegetation types. We've got several different types of thickets, riverine, xeric, valley. We've got grasslands, savanna, oldlands, and charoid. And then just species present on the reserve, we've got the big 5, mega-herbivores, elephant, we've got both black and white rhino, buffalo, springbok, impala, everybody's favorite. And then extra elemental, so non-native species like the white rhino and giraffe. Okay, so just today, I want to go over what we're doing in terms of vegetation monitoring with aerial photography. So all in all, we want to be able to capture baseline data, and I'll get into that of how we've done that with the drone. But to monitor our vegetation, I want to look at quantitative data and qualitative data. We already are doing fault condition assessments every 3 to 4 years. That's on the ground surveys, looking at our grass components and our woody components. And then using that data to calculate our carrying capacities on an annual basis with our annual rainfall, and then we're able to compare our stocking rates with our carrying capacity. So we're already doing that. We are doing our NDVIs every few years, and then we have been doing fixed point photography from the ground since 2017, and then more recently we've incorporated aerial imagery with a drone. These objectives, using these different types of data collection, we wanted to be able to determine successes and failures of our vegetation rehabilitation efforts, the impact of our mega-herbivores, as well as other herbivores, the changes in the vegetation over time, species-specific impact, so vegetation, so particularly today, woody species, any alien invasive density changes over time, and then canopy cover changes over time. Just going to briefly touch base to the vegetation rehab. So we became a protected environment in 2019, where we have to meet annual requirements. So we have to, eradicate a certain number of hectares each year of alien invasive species, bush encroachment, thicket restoration, and erosion control. So what we did is we first did a assessment of the entire reserve of areas that we identified areas that need to be rehabilitated, restoration. So you can see those in the maps. And then before we did anything, any type of rehab, we flew the drone over. So we had the flight plans, flew the drone over so that we could get the baseline. And then after we do the rehab, the different methods, then we'll take a photo again, that same flight plan, and then we'll do that over time at set intervals, just to visually be able to see the changes over time and if those successful or not. And then at the bottom, you'll just see those are just sample photos of erosion and bush encroachment. And then at the top is our fixed point photography from the ground, just as examples. Okay, so that's one way we're using the drone. The next, this is actually quite exciting stuff happening. So this was the map of Amakala pre-August 2024. It was 3 different sections, and the into the national road cuts those top 2 sections with the bottom section, the southern section. So there's no connectivity. You couldn't access animals couldn't move through. Sorry. And we knew that eventually we wanted to expand the land and we wanted to provide connectivity. So that got us thinking. We had a drone used for more anti-poaching and security, and we had the drone, so we wanted to use it for other things. Sorry. So here, in August last year, we opened an underpass through the Bushman's River. And it connected these 2 sections. This section and then this one has not had elephants on it for hundreds of years. So I wanted to try and get baseline data for these 2 sections before we open this underpass. This, we expanded this. It's just under 400 hectares. We expanded that in January of this year. So I wanted to be able to get some drone imagery of these 2 sections before we opened up. And then also there is an old cattle tunnel there that's able to fit a nice game viewer with the roof under it, so connecting those 2 sections. Unfortunately, giraffe and elephant aren't able to move into this section. But now we've got connectivity and we've expanded our land. And this is just examples of, this is just to show you what it looks like. So, sorry. So this is the N2 bridge, old N2 bridge, dry Bushman's River, hopefully not for long. This is our southern section, our northern section, or northeastern section. And then we kind of created a funnel system with the fences. So this underpass is more than exceeded my expectations. This is just camera trap footage that we put in the underpass itself. It took our elephant herd 5 days to go through. And you see our predators, our lion, our cheetah, bushbeck, aardvark, hippo, they've all moved through. What's been really amazing to see is, for example, the elephants didn't just stay on that section that had this pristine thicket, untouched by elephants for hundreds of years. They're actually moving back and forth. They're using this underpass and moving back and forth rather than just having impact on one area. So they're spreading that impact, which is amazing. And then, just to think about connectivity, we're seeing a lot more brown hyena sightings than we did before the underpass, and they're utilizing that underpass. And these previously isolated populations are now intermixing and then increases genetic diversity. And that goes for more than just brown hyena species. So it's been, a really exciting time for Amakala. So with this specific drone imagery project, I wanted to target species specifically looking at elephants. So pre and post elephant, reintroductions for those sections that hadn't had elephants for a while. So I wanted to look at prickly pear, aloe, speckbloom, other preferred elephant forage such as cabbage trees, boulder bean, common guari, and then also look at the canopy cover. So methodology, get a drone. And our dedicated drone pilot. I don't know enough about drones. We are using the DJI Mavic T30 drone with 12 megapixel resolution camera. Again, that means nothing to me, but it is important to have a good camera. So once you've got a drone, then we identified sites. So in the grand scheme of things, it'd be great to be able to have imagery of the whole reserve. That is on the list. Not at the top, though. Many other things to do. So I want to do sample plots. So again, I'm just looking at the 2 areas that we opened up to elephants. And I aim to have 1 hectare size plots. And that's simply because you think of your drone and the battery life. So I wanted fine scale imagery and broader scale imagery. So the smaller plots are 1 hectare plots, 30 meter height that the drone is flown. And then the 100-meter heights, which I think the largest one I've got is almost 12 hectares in size. And yeah, once you identify the flights, and I just did these quickly polygon in Google Earth. I gave them to the drone pilot. He plugs it into his controller, like drone controller, into his laptop. It uploads onto the DJI app. He does all of his settings, and then he goes and flies. It's as simple as that, I guess. And then once he flies all the sites, you will get this. This is just a fraction of the photos that it takes. It takes a bunch of different photos for that one site, and then they need to be stitched together. Thank you, Alistair, and the team. They are using Agasoft. Unfortunately, the stitching software is quite expensive, and we just don't have those resources at the moment. So Alistair and NMU have helped us. And then this is the outputs. So I've just uploaded this in QGIS, and these are just the raw files. And then I just wanted to clean them up a bit, and I clipped them to the actual polygon size that the original plot. And these are the orthomosaics. So this is a 100-meter flight, and this is a 30-meter flight. And when you zoom in, it shows a lot of detail. It's actually quite incredible. So this is where we've gotten so far. Our next step is to put it into artificial intelligence software, the convolutional neural network, CNN. Again, thank you, Alistair. The next step is to actually train this software to be able to identify the specific species that I'm looking at. And then once that happens, then we can start estimating the densities and then looking at those changes over time. So those are next steps. Lessons learned. Don't want everybody to be a guinea pig. I guess I'll be the guinea pig. So planning, definitely need a dedicated drone. We found that because the drone has to fly slow, it does take a toll on the batteries. The height of your flight plan, again, what are your objectives? What are you trying to establish? What are you looking at? The size of your flight plan for the drone batteries, the shape of the flight plan. We learned that square is the best. Rectangular can work, just can't be too narrow. Any other shapes don't work, they get too distorted. Your SD card size, if you're flying low flights, is going to take a lot of photos. So think about that for your drone. And then when you're actually flying those flight plans, you need to know the area. You don't want to run into power lines. It's quite an expensive drone. The best time of day is in the middle of the day in overcast conditions. The overlap size, so again, this is on your preference, but we use 15 meters. So we've got our polygon or our flight plan, and we do 15 meters outside of that. That way that we make sure that our actual plot that we're looking at gets covered properly. And then while you're flying, monitor the controller. That's it. Don't interfere with the flight plan because you're probably going to have to start over. And then as far as the analysis side of things, you need to figure out how you're going to stitch that software. I've used a lot of free trials, different emails. The storage of your the storage and organization of your files, you need to make sure that it's nice and clean. And then at what intervals you want to take this aerial imagery. And I think the most important thing from this is take the photos. Do it now. Don't wait until you're 100% organized, because you never will be. You can take the photos, store them, and then you can work on stitching them and doing the AI at another day, on another day. And then just next steps and takeaways. Like I said, we still need to, train the AI software, and then we'll be able to measure the densities using that software. We'll continue to do the aerial imagery at the set intervals at all the sites. We just did our second round. I would love to conduct aerial imagery of the whole reserve, so we'll see how that goes. And then this is obviously not limited to just looking at elephant impacts. This can answer a wide range of research questions, which I'm looking forward to. So anybody want to do a master's, PhD, come on down. And then once we've done the more in-depth analysis, I would hope that this could help me make active adaptive management decisions using evidence. I don't want to thumb suck when I'm recommending what we should do and not do. I want to be able to use data. And also, lastly, the most important thing is this isn't the tool that we're using. This isn't answering all of our questions or will answer all of our questions. This is one of the tools of how we are monitoring our vegetation and the impacts of our herbivores. Questions?